Dear participants, it is a pleasure to be lecturing at the European Researchers' Night organized by the University of Nova Gorica. My lecture has the title Creative Computer Assistant in Knowledge Discovery from Data. My name is Nada Lavrac. I am professor at University of Nova Gorica and a researcher at Jožef Stefan Institute. Given that we are recording, we have to inform you about the ethical issue concerning the open science. We are recording this session, and if anybody objects, you should let us know. Initially, I prepared the talk in Slovene, but since we have a person who is English speaking, I will switch from my Slovenian lecture to the alternative English lecture, which I have prepared for the case if at least one of the participants was not speaking Slovene. So I start with the English lecture. The lecture is titled Creative Computer Assistant in Knowledge Creation from Data. So as mentioned, I work both at Jožef Stefan Institute Department of Knowledge Technologies, as well as in the Center of Information Technologies and Applied Mathematics at the University of Nova Gorica. So part of the research in these two institutions is concerned with the development of algorithms and applications of knowledge technologies, where knowledge technologies are part of computer science, they are part of artificial intelligence, and the main areas of research being machine learning and data mining, text mining and web mining, human language technologies, decision support, and computational creativity. Actually, you heard already a lesson about decision support by Hashem Borbar, and today in my talk I will mainly focus on machine learning, data mining, and text mining. And this is the lecture overview, starting with machine learning. Then I will address also a very modern part of machine learning research, which is referred to as the representation learning, and I will finish my lecture with text mining. In machine learning, I will cover some basics. I present some standard learning tasks and present 3 generations of machine learning approaches and algorithms. So what is actually machine learning? As mentioned, it's an area of computer science which is concerned with the development of computer algorithms that learn from data. In machine learning, we have some input data, and the output is typically a classification model, which is automatically learned from pre-classified data. So the terms machine learning, this is one of the terms which is used. It comes from early AI research in the 60s and 70s, where we have perceived the learning algorithms as machines, automated machines which are able to learn or generalize from data automatically without human intervention. An alternative expression is inductive learning. It refers to the capacity of learners to generate and generalize automatically induced models from the data. Whereas symbolic learning, which is also an alternative notion used in early machine learning research, referred to the capacity of learners to induce explainable knowledge from data. And on this picture, you see a classification model in the form of a decision tree, which is one of the standard machine learning representations. As opposed to symbolic learning, which aims at inducing explainable predictive models, such as decision tree or classification rules, in sub-symbolic learning or neural learning, which is very modern nowadays, the induced model which can be used for classification, is a kind of black box classifier. It is typically a neural network which gets some input and produces a classification outcome. However, it is not capable of being explained, of explaining its decisions. So in early machine learning research, symbolic learning algorithms were developed, like rule learning algorithms by Michalski in late 60s, early decision tree learning algorithms in early 70s by Ross Quinlan, early regression tree learners like CART, developed by the statistician Bryman, and their advantage is explainable models, but occasionally slightly less accurate classifiers compared to neural learning algorithms or some symbolic learners, including early research on perceptrons in the 60s, backpropagation neural networks in 80s, and nowadays very popular deep learning, deep neural networks from 2006 and now with the boost in 2016, where the advantage is that they are learning more accurate classifiers, but their disadvantage is that their explanation capacity is very, very much limited. So basic machine learning tasks depend on the type of input data and the goal of learning. So if the input is tabular data, we are typically doing prediction and classification. If the data is not labeled, we can do clustering of data in tabular data tables. But then if we go to more advanced representations of data, like relational databases or multi-relational databases, as we name them, we are performing learning tasks like relational learning and sometimes also referred to as inductive logic programming. Further on, if the input to a learning algorithm is a graph or a network, what we can do is network analysis, including social network analysis, or predicting links in a network, or node classification, or network completion, or node labeling. Let's say, suppose part of the network has been labeled with class labels and some nodes are not, then you are trying to label the unclassified nodes. Next, text mining refers to the analysis of texts, and texts are being omnipresent, including short texts in tweets or long texts in documents or scientific publications. In short text analysis, many times we are interested in the sentiment of tweets or hate speech detection and so forth. We're also interested in document clustering and topic analysis and topic assignment. If the input are web pages, we may be interested in next web page recommendation based on the clicks we had on the web until now. But also the input can be even more extensive and more heterogeneous. We refer to it as heterogeneous information networks, where part of the information is in the network format or graph format, but then in the nodes of the network, we can have texts or we can have other information, we can have data tables. In that case, we can perform classification of data instances, node classification, link prediction, and so forth. So these learning tasks were ordered in terms of the complexity of the input data format. And in the simplest case, we have data tables at the beginning as the input to a learner. And what we want to do is learn a classification models, either symbolic or sub-symbolic. And in this little picture, you have a data table about people who came to the opticians and they wanted to get contact lenses, but some of these people did get contact lenses and the others did not. The ones who did got either soft or hard lenses, and some people didn't get lenses because of the properties of the individual. And one could find out that whenever an attribute among the 4 attributes has certain values, the lenses class will be predefined. For instance, whenever a person has reduced tear production, the person didn't get contact lenses. And in that case, we would refer to the learning problem as pattern analysis or pattern mining. And our patterns and the models which we have learned can be either symbolic or sub-symbolic. And their explanations when classifying new instances could be either explainable or simply a black box. So the basic machine learning task is, as mentioned, given some input, build a classification model or find patterns in the data. And here I have again this specific table about patients coming to the optician who the optician would assign some type of contact lens to them or not assign them. And you see the columns correspond to some properties or attributes, as they are called in machine learning. The rows correspond to individuals, to the data instances, or to so-called training examples. And the values in the data table correspond to particular values of attributes or to the properties of the instances. And from these properties, we want to learn a classifier automatically. And here we see one of the possible outcomes being a decision tree, which is read from the top towards the bottom. It starts with the most informative attribute, which will select instances of one class and distinguish them from the instances of the other class. So one property being that if tear production is reduced, no contact lenses are assigned. On the other hand, if tear production is normal, which is another value of the tear production attribute, the decision still depends on other attributes like astigmatism, meaning that if tear production is normal and astigmatism, the person doesn't have astigmatism, it is highly probable that the person will get soft lenses. However, for people with astigmatism, it still depends from spectacle prescription. For myopic people, the majority didn't get hard lenses, did get hard lenses, and for hypermetropic people, mostly they didn't get hard lenses. So this is a decision tree classification model, which can be used for modeling, for predicting the outcome of a new unclassified instance. Alternatively, decision trees can be transformed into classification rules, which basically bear the same information as the decision trees. So the basic definition of machine learning is that learning algorithms are those algorithms which learn predictive models from class-labeled data. But in data mining, also we have the problem of learning patterns from non-labeled data, or also learning patterns from class-labeled data. And we are interested in extracting useful information from data, in discovering some interesting relationships, as well as patterns that have not been previously known. So this pattern, which I mentioned, can be directly induced from the data by simply looking just at one attribute. And such a pattern, if tear production is reduced, then no lenses are assigned, can be induced by an algorithm which is called association rule learning, which is a very popular approach in machine learning. So in this pattern mining scenario, we take the data, we want to induce some interesting patterns like individual rules, and then we try to explain them to the expert and to the user. So standard machine learning tasks are not only the task where we had multiple classes in the target attribute, Here we have binary classes, just no and yes. This is referred to as binary classification problem. And we have positive and negative examples of the target class. And this is used in many scenarios, including subgroup discovery, where we are doing pattern mining. We can have several class labels, like in the initial use case, which I explained, where we have 3 classes for the target attribute. We can have so-called multi-target classification, where at the same time we would like to predict several classes, like if somebody will get lenses, or if somebody is pilot by profession. Or we can have numeric class targets, and we want, in that case, to predict a specific value for a new instance to be classified. And in that case, we refer to regression problems. And here I have a very small illustration of a regression problem where we have age as an independent attribute and height as a dependent attribute. And for a new person of a certain age, we would like to predict what is the height of this person. So if we plot the data on 2D, we see such a regularity. And then if our baseline numeric model would be the average of the target variable, for every age, we would just predict the average, which is something about 165 meters height. On the other hand, if we would do a better model, it would be a linear regression model, which is a linear line connecting the age with height, like a coefficient times age plus the coefficient 1.4. And this would be a better predictor compared to the previous, but then we can learn also regression trees, which are similar to decision trees, but they are predicting a numeric value in the decision tree leaves. Or we could have even a better predictor being a model tree, where in the leaves of the decision tree we have linear regression lines. So such a predictor would be even better compared to the previous ones shown. A direct algorithm for predicting the class from the data could be k-nearest neighbors predictor, which assigns the class to an individual based on the 3 nearest neighbor classifications. We would evaluate classifiers in terms of their accuracy when predicting new instances. So the first generation machine learning algorithms were characterized by learning from small data tables, both in terms of instances and numbers of attributes. But then after the first generation, in the 80s, a lot of new research was performed in the 90s, and the new term appeared like knowledge discovery in databases, which started focusing on the entire process of knowledge discovery, starting from the data itself, selecting the data for the analysis, data pre-processing, data transformation into a form which is applicable for a machine learning or data mining algorithm, and finally evaluation. And it is an iterative process which can go back if the outcome of learning is not satisfactory for the expert. So knowledge discovery in databases, or KDD, became a buzzword at that time. And the focus was still on machine learning step, but also on the entire process of data preparation and analysis. And many new tasks were starting to be of interest, like association rule learning, which I mentioned before, subgroup discovery, or relational data mining, where subgroup discovery starts with the binary classified data instances, and the task is to find different rules which cover the target class. They can be either overlapping or non-overlapping. They can either be pure in terms of covering just the target class and none of the negative examples, and the set of rules is constructed, but each of these rules is considered as being a separate pattern. On the other hand, in relational data mining, the input is a relational database, and we are again trying to find interesting models or patterns in the data. Alternatively, to a set of tables at input, we could have also sets of logical facts or graph or a network. And in second generation data mining and machine learning, first very useful platforms started being developed, including Orange, developed in Ljubljana, Faculty of Computer Science, Weka, developed in New Zealand, Nine, developed in Germany, RapidMiner, also a German development. And the nice thing about them was that they, first of all, included a lot of machine learning algorithms, but it also had a very good facility for data and model visualization. Furthermore, they allowed so-called workflow construction, where you can build repeatable workflows for the scientists to do exactly the same pre-processing steps and modeling steps, which then contributes to open science and repeatability of experiments. In the late 2000, big data started to be a buzzword, which refers to data and techniques for dealing with very large volumes of data and possibly dynamic data streams. And the characteristic is that the approaches for dealing with such large volumes of data would require also large storage resources, special algorithms, and also the facility for parallel computing. Big data is characterized with 4 V's, like volume, which refers to a large scale of data, variety, meaning that data can be heterogeneous of different types, veracity, meaning that data is not necessarily certain, but we can deal with uncertainty of data, and velocity, referring to data streams. So data can come one after another in time series. Suppose we have sensor data and we have to analyze large data sets coming from sensors. A further buzzword starting in 2012 is data science, which is now extremely popular as the buzzword. It came with the Harvard Business Review paper, where the engineer job of data scientist would be the sexiest job of the 21st century. It is referred to as interdisciplinary field, which uses scientific methods, processes, algorithms, systems to extract knowledge and insights from data in various formats, both structured and unstructured. And in this way, it is similar to machine learning and data mining. And this expression, data science, is used interchangeably in many ways with earlier concepts like business analytics, business intelligence, predictive modeling, as well as statistics. So it is simply a buzzword which covers all aspects of data analytics. And now in the final third generation machine learning, which has been developed since 2010, the focus is indeed on big data analytics. The focus is on addressing complex data mining tasks and scenarios involving heterogeneous data. Many new conferences have started appearing, and new learning tasks started appearing, like learning from dynamic data streams, network analysis, also semantic data mining and text mining, which are partially covered in this lecture. But also the focus started being also on this transformation step, which was identified already in the KDD process. But now there is a lot of focus on data transformation when transforming the data from heterogeneous formats to a simple tabular representation, which is most frequently used in machine learning and data mining. So this transformation step is recently referred to as representation learning or embedding. So representation learning actually concerns automated data transformation, which is performed on pre-processed data, because sometimes you still need to do some manual data pre-processing before you start automated data transformation. And data transformation techniques require handling heterogeneous data, where the data are either feature vectors, documents, pictures, data streams, but also some additional background knowledge, which can be included in the learning process. So background knowledge typically refers to the expert knowledge which helps the data mining process to induce better classifiers and to find more understandable patterns. So such additional background knowledge can be found in relational databases, but as well as in networks, in text corpora, as well as in big taxonomies or ontologies, which can be used as additional knowledge to a machine learner. So if we look at the representation learning step for advanced learning tasks, which is a very modern part of machine learning, and we look at it, how can it be done for relational machine learning, for semantic machine learning, as well for text analysis. So in these scenarios, we have either a multi-relational database, or we have very complex data like chemical molecules, which are composed of atoms. Molecules have some properties as well as class labels, but atoms can also have some properties, and the atoms are connected to each other with single or double bonds, and the molecule can consist of several atoms which are connected with one to many relationships, denoting that it's several atoms per molecule. And what is the transformation step here? Symbolic transformations are referred to as propositionalization, whereas subsymbolic transformations are referred to as embeddings. In both cases, we take some data, like a relational database, for instance, and we transform it into a single table representation where each data instance is transformed into a single feature vector. And how does propositionalization, symbolic transformation from, for instance, multi-relational data to a single table presentation, how does it look like? It takes the target table. For each target table instance, one row in the transformed table is composed, and in the rows, we will have zeros and ones, one meaning that the feature which has been automatically constructed from the multi-relational database, the feature is either true, value 1, or the feature is false, value 0. So such features could be logical features which could be composed from several properties of a multi-relational database. And now that we would have such a transformed data table, we could use any machine learning algorithm on top of that to learn a classifier, for instance. So propositionalization is referred to as symbolic data transformation from either complex multi-relational databases or complex networks or complex graphs. And data mining would refer to finding interesting patterns in such transformed data tables. So let's look at semantic data mining, which is one special case of relational data mining. In semantic data mining, our situation is as follows, that we can have either single tables or multi-relational databases as data of experimental data to be analyzed. But in the background knowledge, we can have hierarchies, which are referred to taxonomies, or even ontologies. And ontologies are even more complex data structures. So as mentioned, in semantic data mining, we have the data as well as, let's say, taxonomies or ontologies, and we should have some annotations between or mappings between the data and the concepts in a given ontology. So ontologies are known in science for a long time. Let's say if we look at biomedical data, we have a famous gene ontology, which is a database of terms describing gene sets in terms of their functions, properties, and components. And we have hierarchical relationships between them, like connections is part of or is a, and the levels in such structures represent generality of terms, where each of the gene ontology terms refers to a set of genes with certain properties. In semantic data mining, it turns out that we can also use propositionalization or flattening approach to transforming such complex structures into single data tables. And also in text mining, it turns out that we can do this kind of flattening of documents or texts into simple data tables of vectors with 1 and 0. And in document representations, we are not using complex logical features, but individual words which appear in documents will get value 1, and the words which do not appear in the document get value 0. And the set of all the n features correspond to all the n words which appear in the entire document collection. The representation in such tabular format for a data collection of text documents is very frequent, and each vector or each row in such a data table is called a bag of words representation of an individual document. And I will explain how this is done. So let's look at the entire text mining process. Usually, what we do with texts is we first start with some document pre-processing steps, then we do this vector construction from individual documents, and then we construct a table of these vectors, and this data table is then used for by some machine learning algorithm, which is capable of doing classifier construction for the tasks like document categorization, clustering, summarization, and so on. So in the picture, we see a data collection of documents, of texts, and then maybe we would like to classify each of the documents into one category like technology, sports, or fashion. In pre-processing, we first do tokenization. We convert text to a list of tokens like words or two consecutive words named bigrams. Then we do stop words removal. We eliminate some very frequent words like prepositions a and the, because they have no semantic or lexical information carried over for the task of classification. Then we do part of speech tagging. We can do lowercase transformation of words, and then we do lemmatization and stemming. The reason is that different form of words are should actually be represented with a single word, which, for instance, if we have words like I am, he is, we are, am, is, and are should be transformed into a single word, meaning to be, for instance. Or in Slovenian, we can do lemmatization by replacing the word suffix with the word from suffix from the normalized form. Like ja se smejem, ti se smeješ, mi se smejemo is transformed into the form smejati, that is the word to laugh in Slovenian language, and this would be a word which would appear in a vocabulary or in the dictionary. An alternative approach to normalizing words is by stemming, which is transforming words into their stem by chunking off the suffix. Like cats would be transformed into cat, working would be transformed to work. And there are algorithms which can do it easily for English language, but also for Slovenian. We have stemming and lemmatization algorithms which have been developed by local researchers. So there are some rules how to start data processing and which steps should be done first. And then this bag of words representation is also referred to as one-hot encoding of dictionary terms. For each word, we can represent it with one vector. So this would be the encoding of words. On the other hand, the encoding of documents, we would have value 1 for every word which appears in a given document. So suppose we would have the sentence, Tina lives in a house, which would constitute a short document. So for words house, lives, and Tina, we would have value 1, and for other words, we would have value 0. How are we doing with time? I think I'm at about 30 minutes. Is that the case?
Yeah, if it's possible.
Okay, so I have some more time to do the explanation of this transformation of documents into vectors of words. Let's say if we have the document, it's a short document, the quick brown dog jumps over the lazy dog. We have the following words in this document: quick brown dog, jump, lazy dog. And if we would transform it into the bag of words, we would have 1, 1, 1, 1, 1 for the all the words. But here the word dog appears 2 times, and one of the ways how to weight, to assign weights to the words would be simply computing the word frequency. So instead of taking into account the dog 2 times and putting it into a vector which would be 6 units long, we have a vector of 5 units long, and we put the weight 2, which is simply a count of the number of times the same word dog appears in the document. Suppose we have another document. This is another lazy person. Another lazy person would be the relevant words to be used in the bag of words document representation. Is chunked away because it's not very important, because it's a very frequent word, and very frequent words which appear in all the documents are usually taken away. This is also not a very informative word. So another, lazy, and person are the 3 words which the algorithm considers being sufficiently important. And then if we look at the document collection, we have 2 documents, which means 2 rows in a table. In the first row, we have 1, 1, 2, 1, 1 for the first 5 words. And in the second one, we have 0, 0, 0, 0, 1, 1, 1 for the words lazy, another, and person. So lazy appears in both documents, so it gets value 1 in both rows of the transformed tabular representation. So this illustrates the so-called term frequency weighting of words, which simply refers to counting the number of times a word appears, but a much more frequently used representation is so-called term frequency inverse document frequency. So in this weighting, we have the term frequency, which means counts of the number of times a word appears in a given document. However, we have another part, which is inverse document frequency. So the idea is that we would reduce the weight of the word if a word would appear in very many documents. So if a word appears in all the documents, it doesn't make sense to take it into account because it has no information for a classifier to select, to distinguish when distinguishing between two different classes. So TF-IDF is the relative importance of the word in the document, where this IDF is computed by looking at the document frequency, so number of documents containing the word, and if it is large compared to the entire document collection, the weight of the word should get reduced. And this is actually the TF-IDF measure, which is used in all the standard text mining approaches. And if we have, let's say, two documents, we can start computing the similarity of the two documents, and the similarity measure can be used, for instance, in clustering of documents when, for instance, applied to topic analysis. And the similarity between documents can be computed with a number of different similarity measures, but the most popular being the so-called cosine similarity between two vectors. And if the vectors are unit vectors, this is the top formula applies. On the other hand, if the document vectors have been weighted with TF-IDF weights, this is how we compute similarity between vectors, or in other hand, similarity between documents. A modern approach is to representational learning in text analytics is so-called text embedding. And we can do either word embedding or sentence embedding or document embedding or corpus embedding. And again, the transformation is into a tabular format, but now we don't have as many columns as there are words in the entire document collection, but we have a pre-selected number of dimensions here. And we will see what are the dimensions, but typically the dimensions would be very low dimensional space, either 64 or 128 or just several hundreds dimensions, but not thousands and thousands dimensions like in the word representation of documents. And with these dimensions, we can get much more compact representations of documents. So if we look at the document embeddings, the table values correspond actually to the weights in the embedding layer of a deep neural network. And neural networks are very good at modeling similarities of words or similarities of documents. So it is a very modern approach to text analytics that instead of bag of words representation, you do this embedding representation of documents into a much more compact representation. So what could be the interesting text mining applications? They can be document clustering and topic identification, document classification and categorization, document anomaly and outlier detection, sentiment analysis in tweets and other social media, authorship attribution. So we have a document and we have a number of possible authors. The author is unknown. So from previous texts of the same authors, we could kind of, based on the writing style, attribute the authorship to a new document. We could do web page recommendation, web user profiling, and so on. So categorization or classification could be seen with the metaphor. We have some documents on the left-hand side picture, and we would like to put it in folders, and we would like to label them by a topic category. We can do it by using pre-classified documents. So we know for a number of training examples what category they belong to, and then we use a learner to build a classification model from text data.
In 1 minute, you can finish it. Thank you.
I didn't hear you.
Just 1 minute, if you can finish, please.
Okay, I will finish in 1 minute. Clustering applications are also very interesting. And for that, we can use K-means clustering algorithm, which is illustrated in this slide. In summary, I have very briefly presented machine learning as an area of artificial intelligence research. I have shown some very basic illustrative examples and presented 3 generations of machine learning and data mining methods. I also have addressed representational learning as a modern technology for transforming data into tabular format, either with 0-1 representations or dense embedding representations. And I have very briefly presented text mining for the analysis of texts, where document clustering can be used for topic analysis and topic modeling. With this, I will stop this presentation. I will also stop the recording of this lecture.
Thank you very much. It was very nice and very beautiful. There is any question from Eric or Luca, please.